Right, this is the second lesson, grade 11's, on the hyperbola. So basically we've done a summary of what the function looks like, what the formula looks like, and now we need to make a summary of how to plot it. Now just to start, don't forget that not every hyperbola can be written like this. It doesn't have to be written like this, and so when we do the past papers, we'll see how they can spice it up, but every hyperbola can be written like that. So the first thing to notice, just a summary, we've said this before. Let's actually do A is positive first. So don't forget that there's two shapes to a hyperbola. If A is positive, we have the shape where we have one of the branches in quadrant 1 and one of the branches in quadrant 3. And if A is negative, you have one of the branches in quadrant 2 and one of the branches in quadrant 4. So to be honest, I just remember that because it helps me quite a lot. When I'm looking at whether I'm trying to plot, it helps me quite a lot to see what it visually should look like. So there we go, two shapes, and I've said this quite a number of times, but to go from one to the other is a reflection over the x-axis. So these two actually are related. Okay, so the moment we're going to plot, when we go into our examples, the moment we're going to plot, we must figure out, are we doing A positive or A negative, and so what shape it is. Right, moving on to our asymptotes. Remember, the asymptotes in a hyperbola are the two lines, there's one vertical and one horizontal, that the graph tends towards, but in a hyperbola it doesn't touch it. So where does a vertical asymptote occur? A vertical asymptote occurs at x is equal to p. So if you go up to my formula, there we go, that is what tells me about a vertical asymptote. Now, why does it happen at x is equal to p? Because of the idea that the original parent function had an asymptote at x is equal to 0, and then basically you move this left or right, and then move this left or right. So when we do examples again, we're going to concentrate on what is the sign of the p, and therefore how do you know if it's x is equal to positive 2 or negative 2, for example. So when we do an example, we'll have a look at that. Also, just remember, why does this occur? This occurs because your denominator cannot be 0. So if you're ever stuck, just say to yourself, my denominator can't be 0. So that means x can't be p. So x is equal to p is your your vertical asymptote. So we'll discuss that more when we come to an example. What's our horizontal asymptote? Our horizontal asymptote, if I scroll up, is this q. Remember, it started off at y is equal to 0, and if you move the graph up or down, your asymptote also moves up or down. So you have y is equal to q. Right, so now that we know our asymptotes and our shape, the next two things that you should label if they exist is a y-intercept and an x-intercept if they exist. Now, why do I say if they exist? If I look at my original functions, my original function looks like that, or my original function looks like that, depending on whether it was a positive a or a negative a. So the original functions have no x and y-intercept. So what would you have to have in order for a y-intercept to exist? You have to have moved the original graph up or down. Because if they didn't move up or down, not up or down, being silly, we would have to move the original function left or right. If you move the original function left or right, then the graph will land up cutting the y-axis. If you don't, the graph doesn't cut the y-axis. Now, fortunately, you just let x be equal to 0, like we find every other y-intercept in the whole wide world. But just don't be alarmed if we don't find a y-intercept, because if the graph didn't move left or right, the y-intercept doesn't exist. Now, similarly with an x-intercept, only if we move the graph up or down, then the x-intercept would exist. So again, rather think about it before you try and find it. It might not exist. Fortunately, if it does exist, it's very easy to find, because like with every other x-intercept in the whole wide world, we just let y be 0. Right, now the next thing is, when we plot a function, we always want to have one point on each arm. Now there's two, I call them arms or branches of the graph. if we plot the A positive, you've got that branch and that branch. If you've got A negative, you've got that branch and the second branch. Now we try to always make a point on each branch. So if, for example, this entire graph moved down, then our asymptote would have moved down, and this branch would move down, and that branch would move down. Now, this part of the graph is therefore great. You've got an x-intercept that you can plot for accuracy, and that looks great. However, this second branch in this third quadrant, I call it the naked branch. Now, it's naked because it's got nothing important on it. So, if there isn't an important point on it, how we find a point is we say let x is equal to, and then we decide. Now, we shouldn't really just pick anything, because if we said in this case let x be 1, we would get a point on the part of the graph that already has a point. So in this example, we would want to pick any x's less than 0 in order to plot a point on this particular branch. So we'll also try some of those when we practice, just to see, because it's always nice to have 2 important points on a branch. Now, something I haven't brought into any of these notes yet, and something we're going to have to discuss quite carefully, is don't forget that every single hyperbola has 2 axes of symmetry. So I'm going to go draw them in on my originals. One of the axes of symmetry is y is equal to x. Another one of the axes of symmetry is y is equal to negative x. Now, when we do our examples, I'm going to show you how we go and find those equations, because if the graph got moved left or right, up or down, those axes of symmetry have to move left or right and up and down. So we'll see that when we do examples. So this is basically a summary. We need to know our shape, we need to know our asymptotes, and we need to be able to find our intercepts if they exist. So let's go look at the exercise together. We're also going to find the axis of symmetry, which they haven't asked for, because we do need to practice that. So let's have a look. It says plot the following graphs on the axis given below, labeling all intercepts and asymptotes. Now, just be aware that when they say on the axis below, in a test or exam, they're not going to give you an axis. But to be honest, I find it so much easier not to have an axis, because then I don't have to worry about my scale. Okay, so if I saw this in an exam, what would I want you to notice immediately? Immediately, I would want you to go, great. This is a negative, so immediately I know that my branches are in quadrant 2 and 4. Okay, but this graph went and moved 1 unit, careful, minus. This graph went and moved 1 unit right. Now, if it moved 1 unit right, it means that this vertical asymptote, which should have been at x is 0, now moves 1 unit right, and it's going to land up at x is 1. Now, we'll discuss that again in a second, but hopefully you're convinced that the original function would have had a vertical asymptote at x is 0, and so if everything moved 1 unit right, your asymptote moves 1 unit right. Now, the moment the graph moves 1 unit right, my function will now cut the y-axis. So I am expecting a y-intercept. But careful, it didn't only move 1 unit right, it moved 4 units up. And the moment it moves up, my horizontal asymptote, which should have been at y is 0, now goes up to y is equal to 4. So before I've even started my function, I know that I moved across and up. So what do you know? I am expecting an x-intercept, and I moved across and up. So I am expecting a y-intercept. Now, I like to plot that on my question paper, not properly, but just so I can figure out, oh gosh, I am expecting my intercepts. So if I am expecting my intercepts, let me go and find them. So what's true at every y-intercept in the whole wide world? X is 0. So what is the function value at 0? It's negative 2 over 0 minus 1 plus 4, which I would really use a calculator for if you didn't like it, but I got 6. So if they asked me for my y-intercept, I would say 0, 6, because remember, it's always a point. Now, if I look at my rough sketch, that means that's 6. Now, that makes complete sense, because my horizontal asymptote is at 4, and so it does look like my intercept needs to be above that. Okay, how do I find my x-intercept? Well, my x-intercept is I make y 0, so 0 equals negative 2 over x minus 1 plus 4. Now, this is why in grade 8, 9, and 10 we make you do so many fraction equations, because now we're going to start using it. So I don't like to multiply out initially. I would bring my fraction to the other side, which means notice I've changed the sign. Now the reason why I do that is because I'm sure you'll remember that with a fraction equation, you need to multiply both sides by the denominator. Now, if I've got one thing on each side, it's much easier to multiply. If I multiplied in this line here, you would have to multiply every term by the denominator, and most people forget to multiply each term by the denominator. So that's why I find it easier not to do this in this line, but to rather make one thing on each side, and then to solve it from there. So now what happens is my x minus 1's cancel, and I get 2 is 4x minus 4. I take my 4 over, 6 is equal to 4x, and divide by 4, and I used my calculator because 6 divided by 4 is 3 over 2, which is 1.5. So all this tells me when x is 1.5 or 3 over 2, I have my x-intercept. Now again, that makes sense because if you look at that, my vertical asymptote is at 1. So it does make sense that my intercept would be slightly bigger than that. Okay, so before I find my axis of symmetry, I'm just going to go and plot this I'll show you in a second of what I do in a test or exam. So first of all, I need to we always plot asymptotes with a dashed line, and you must label it, not 1, x is equal to 1. An asymptote isn't a number, it's an equation, it's a line. Then we have y is equal to 4, which is my horizontal asymptote, which I'm going to label. And then I had x is 1.5, so you kind of guesstimate where it is. You can write 1.5. Don't forget that if something's an intercept, you don't have to write both coordinates. As long as you write the one coordinate, everyone else knows the other one is 0. And then I make a 10 towards my asymptotes. And my other intercept is at 6, which they've already labeled for me. And I 10 towards my asymptotes. Please don't do the following. Don't draw it like it's, turning back on itself like that. Lots of people end up drawing this. It doesn't turn back. It must, tend towards the asymptotes. So try not to draw that. And there we go. It's generally worth about 4 marks because we did do quite a bit of work. Okay, now let us look at our axes of symmetry. The original graph would have had an axis of symmetry at y is equal to x and y is equal to minus x. That would have been the original graph. Now the problem is the original graph isn't this. The original graph got morphed to form this. The question is, how did it get morphed? It moved right and up. So if your original graph moved right and up, your asymptotes have to move right or up. So your asymptotes should have both gone through the origin, except they're going to go 1 unit right and 4 units up. Exactly what the graphs did. The graph moved 4 units up and 1 unit right, so the asymptotes must move 4 units up and 1 unit right. So I'm just going to write myself, not the asymptotes, sorry, my axis of symmetry. So I'm just going to write myself a note here. So I'm going to say note, whatever transformations happen to the graph happen to the axis of symmetry. So whatever transformations happen to the graph, the same transformations happen to the axes of symmetry. Also, I'm running out of space there. Transformations happen to the axis of symmetry. Now there's 2 of them, so that's why I say axes, plural. Now what were these axes of symmetry in the original? They were y is equal to x or y is equal to minus x, except now they're not going to be because they have moved 1 unit right and 4 units up. So they're going to look that enlarged. So they're going to look something along the lines of that. Oh, those aren't particularly good lines, straight lines, but anyway, something along those lines will be your 2 axes of symmetry. Now just convince yourself for a second if you look at them. I haven't drawn them particularly well, but if I look at them, they do look like if you folded the graph over, you'd get over the axis of symmetry, you'd get the other part of the graph. Now the question is, what are their equations? Okay, now there's 2 ways to find these equations. This is y is equal to x. Okay, now it's still y is equal to x. It's still y is equal to 1x, because I haven't changed the slope of the graph, but I've changed the y-intercept. So I'm going to write plus d. And this graph is y is equal to negative x. I haven't changed the slope, but I've moved it left and right and up and down. So I've changed my y-intercept. Now I have no idea what this y-intercept is yet. But most importantly, my gradient didn't change. I still have y is equal to x. You didn't change the gradient, and you never ever change the gradient in the axis of symmetry. It's just that I need to know what is c and what is d. Now there are two ways to find the axis of symmetry. The first way is to think to yourself, well, when I only have one unknown in an equation, that's very easy. I sub in a point. And what is the only point that both these axes of symmetries go through? Both of these will go through where the asymptotes intersect. So both of these go through the point of intersection of the asymptotes. And that is 1, 4. So this is where your asymptotes meet. Now, I prefer this method of doing it because it's very easy. If you have one unknown, you substitute a point in. So for example, if I look here, when y is 4, x is 1, and I solve for c, and I get 5. So now I know that that axis of symmetry is negative x plus 5. Very easy, sub in a point. If I go to the other one, y is 4, when x is 1, and d is 3. So y is equal to x plus 3. So you can see I didn't particularly draw them very accurately. So that's a very easy way to do them. Simply realize that the point where the asymptotes meet is a point on both axes of symmetry. Okay, the next way to do it I'm going to do in the bottom of this graph here. Every now and again I find this useful. I know that my axes of symmetry are y is equal to x or y is equal to negative x. And all I need to do is I need to translate both of these 1 unit right and 4 units up. So if I translate this 1 unit right, it means that whenever x is x, I must say x minus 1 and 4 units up. This one I must translate, so it's negative, and instead of saying x, it's x minus 1 plus 4. Now the only problem is people tend to forget these brackets. Remember, whenever x is, you must change it to x minus 1, so that negative applies to the whole thing. Now, what's quite nice is that then if I multiply out, I get x minus 1 plus 4 is x plus 3, and what do you know? That's exactly what my other axis of symmetry told me. And over here, if I multiply out, I get negative x plus 1 plus 4, and what do you know? It's negative x plus 5. Which is exactly what I got in the other way. So this method is simply by translating the axes of symmetry in exactly the same way as you translated the graph. So a very commonly asked question, and just pick which method works for you. So this method was translating the axes of symmetry exactly the same as the graph. So when we practice these in our next example, I'll do both methods. Okay, on to the next one. We're drawing this. Y is equal to 1 over x plus 2 minus 1. So if this is me in an exam, I would immediately on my question paper go right. This is positive, so my graph is there and there. Excellent. But hang on one moment. I clearly moved 2 units left. And if I move 2 units left, my asymptote will move left, so I get x is minus 2, and we'll discuss that in a second. I must have moved 1 unit down, so it's y is equal to minus 1. So if I think about this, I need to move left and down, so I'm going to get that, and left and down, I'm going to get that. So am I expecting x and y intercepts? Yes, I am. There's an x intercept, there's a y intercept, but what do you know? I've got a naked branch, so I'm going to have to deal with that in a moment. Now let's just pause for a second and have a look at this denominator and remind ourselves, why is it x plus 2 gives you x minus 2 as your asymptote? One of the ways to think about it is that x plus 2 is not allowed to be 0, which means x is not allowed to be minus 2, therefore x equals minus 2 is my asymptote. That's one of the ways to think about it. Another way is to think that x is equal to 0 was the original asymptote, and I moved 2 units left, so it would go to minus 2. That's the other way. So now, clearly all I need to do is work out my x and y-intercept, and then I'm a for a way. So my y-intercept should be fairly easy. I make x 0, so I get 1 over 0 plus 2, which is 1 over 2, minus 1, and I get negative a half. So 0, negative a half. If they ask for a coordinate, this is just negative a half. Now, also remember that if I ask you to draw the graph, I'm actually never marking you working. I'm just marking the graph. So as long as your graph is neat, I can give you all the marks. Okay, how do I find my x-intercept? I make y is equal to 0. So 0 is 1 over x plus 2. Now again, I would make sure that I have one term on either side. So then when I multiply by this denominator, I don't mess it up and make a mistake. So I'm going to multiply this side by x plus 2, as long as I multiply that side by x plus 2, and they cancel. So I basically land up with x plus 2 must be 1. So x must be minus 1. So all of this tells me that it's minus 1, 0. Now again, that looks plausible in my picture, because I was expecting a number bigger than minus 2 but being negative. So that makes quite a lot of good sense. Now my only problem is there I've got the naked branch. Now we shouldn't really have a naked branch, so I need to say branch. I need to say let x be equal to, and I need to pick any number in the whole wide world. But I'm going to pick any number less than minus 2, because minus 2, after minus 2 begins the other part of the hyperbola. So why not? Minus 3, that's the next one. So f of minus 3 would be 1 over minus 3 plus 2, and I'll just use my calculator. But basically that ends up with negative 2. So I know the point negative 3, negative 2 is on my graph. So let's go and plot this all quickly. In an exam, I would never give you an axis, and I actually prefer it because, have a look, this axis looks slightly silly, because this y-axis is so close together that when I write y is equal to minus 1, it's going to be tough for me to draw. So y is equal to minus 1, x is equal to minus 2. Don't forget to always label your asymptotes with a dotted line. X is equal to minus 2. I think that my intercepts were at negative 1, which is there, and negative half. Can you see how hard it is to draw this? Because this is just a silly scale, which is why I prefer to draw my own scale, negative a half. So my graph looks something like that. Now you notice I stopped quite quickly thereafter because I didn't want the graph to look like it was going flat. And then negative 3, negative 2 is a point on the naked branch, which also looks like it makes a lot of sense. Tends towards the asymptote, tends towards the asymptote. Now, just so you know, in an exam, this is how I would draw it. Remember, you don't have to worry about scale too much. So I would literally draw x is equal to minus 2, y is equal to minus 1, and then I would just draw. And you don't have to stress too much. I'd put a dot there and write minus 1, a dot there, write minus a half there, and I'd put a dot there and write minus 2, so minus 3, minus 2. So that's exactly, that took me all of 3 seconds to draw because it's quite quick. So I actually prefer when they don't give me axes to do it. Now the only thing I'd want to do now quickly is to can I find my axes of symmetry? Now don't forget, my original axis of symmetry should have gone straight through there and straight through there. Okay, now they're not going to do that now because I have moved this graph 2 units left and 1 unit down, which means my asymptotes are going to go straight through my point of intersection of my two asymptotes. So this is going to be y is equal to x plus d, and this is going to be y is equal to negative x plus c. So first method would be to go and substitute in my, not that point, sorry, the point is negative 2, negative 1, my point where my two asymptotes meet each other. So if I have y is equal to x plus d, I know that the point of intersection is when y is negative 1, x is negative 2, and I get d is 1. So therefore y is equal to x plus 1 is one of my axes of symmetry. Note I definitely didn't draw to scale. And then negative x plus c, if I substitute in exactly the same point, just careful, it's negative 2, which actually becomes negative 3, I think. So y is equal to negative x minus 3 is my other axis of symmetry. Okay, what other way could we have done it? Or we could have said my one graph is y is equal to x, my other axis of symmetry is y is equal to negative x. Now whatever transformation you did, so I went 2 units right, 1 unit down, let me zoom out of it, I went 2 units left, sorry, did I say right? 2 units left, 1 unit down. So there's my 2 units left, 2 units left, 1 unit down, 1 unit down. And if I collect up like terms, I get x plus 1. Here I have to do a little bit more work. I have to distribute my minus, and I get y is equal to negative x minus 3. And that's exactly the same answers. So just two different ways to do the same question. Now, we love to ask axis of symmetry questions. So do make sure that you like one of those methods and pick one of them to understand. Okay, now that's pretty much the end of plotting a hyperbola. We'll practice a lot of these in past papers because they do like to ask plotting a hyperbola, and it should be a fairly easy question for us. But first, the next video we're going to do is we're going to do equations from graphs of a hyperbola, and after we've done the exponential, we'll put it together in past paper questions. Okay, well done.